Hello, so in this video we'll cover all of the questions pertaining to the Unit 6 material, which was all about the mole. So that's going to be questions 27, 28, 29, and 30. Now Unit 6 is really a precursor to Unit 7, which is stoichiometry. So they are very, very closely linked. They are very math heavy, so make sure you have a calculator handy and make sure you have a periodic table as well. Okay? So, starting with question 27, it asks you to calculate the molar mass of each of the following. So remember, the molar mass is, like it says, the mass of 1 mole of something. So remember, a mole of something, just since it says it up here, a mole of something is 6.02 times 10 to the 23rd of whatever it is you're counting. So let's just say items. Just like a dozen is 12, a mole is 6.02 times 10 to the 23rd of something. So for each of the examples here, I want to know if I had 6.02 times 10 to the 23rd molecules of this, which really it's technically a formula unit, but you could use either. If I had this many formula units, what would the mass of that be? Same deal with this one and this one, okay? So how do we calculate that? Well, we need the periodic table, and what you need to do is look up the mass of each of the elements in each of these things, and we'll add up the total mass contributing from each of the elements. Now, what you need to take into account is when you have more than one of an element. So, if I look at A, looking at this one, I have 1 hydrogen, I have 1 nitrogen, and then we have 3 oxygens here. All right, so now that we know how many of each element we have, what we need to do is look on the periodic table and find the mass of each of these elements. Now, depending on your teacher, they might do it a little bit differently. I always tell my students to round the masses to 2 decimal places, but do whatever your teacher told you. So, the mass of hydrogen off the periodic table is 1.01 multiplied by 1, because that's how many we had, plus the mass of nitrogen off the periodic table, which is 14.01 multiplied by 1, because that's how many we had, plus our mass of oxygen, which essentially rounds to 16, multiplied by 3, though, because there were 3. So if we add all these totals together, we get that our molar mass for HNO3 comes out to be 63.02. And remember, your unit for molar mass is grams per mole, right? If it's molar mass, you need a mass unit and you need a mole unit, right? So there's our whole piece there. So that would be our final answer for A. Okay? Now, if we look at B, we're going to do the same thing. Notice we have 3 nitrogens, 1 phosphorus, and 4 oxygens. So let's do that. If we take the mass of sodium off the periodic table, which is 22.99, multiplied by 3, plus the mass of phosphorus off the periodic table, multiplied by 1, because that's how many are there, plus that mass of oxygen again, but multiplied by 4, we see that our molar mass for sodium phosphate comes out to be 163.94 grams per mole. So there we go. And last but not least, we take our molar mass of calcium multiplied by 1, because there's only one of them there, plus the mass of oxygen multiplied by 2, because remember that 2 distributes, plus our molar mass of hydrogen multiplied by 2, because again that 2 distributes, and we would see that our molar mass of calcium hydroxide comes out to 74.10 grams per mole. Now, molar mass is going to be very fundamental for the next few questions, because remember, even though if we're just writing the molar mass, we can write it like that, it would be equally correct if we wrote that as a conversion factor like this. 74.10 grams equals 1 mole. And that's how it's going to be useful for us in the next few questions. So now let's move on to question 28. Okay, so for question 28, it asks us to convert 123 grams to moles. Now, 28 and 29 are both what we would call mole conversion problems. We're going to be using dimensional analysis, and we're going to use some conversion factors to change our units around a little bit. Now, there were only 2 possible conversion factors we were using in this section. Either you were using the molar mass, so let's just remind ourselves of these. You were either using molar mass as a conversion factor if you saw words like grams or mass. So there you would write 1 mole equals whatever the molar mass was in grams. Or you were using Avogadro's number. And Avogadro's number was used anytime you saw some sort of particle word like atom, molecule, ion, formula unit, anything like that. So if you see any of those words, you would use this conversion factor. 1 mole equals 6.02 times 10 to the 23rd of whatever the particle was. Again, that would be like ion, atom, molecule, formula unit, etc. Okay? So if we look at 28, we see that we see the symbol for grams, which means we're going to have to use the molar mass. So let's jot that down as a reminder to ourselves. We don't see any sort of particle words, so that means this is going to be a one-step problem. We're just going to convert grams to moles. If we look at question 29, I don't see grams or mass, but I do see molecules, which means we're going to need to use Avogadro's number for that problem. Again, it's going to be one step, but we'll be using a different conversion factor for that. If we had seen both grams and molecules in the same problem, then it would be 2 steps, but I won't need that for this one. Okay, so make sure you jotted down what I wrote in blue if you want that as a hint, because I'm going to erase that so we can get to our actual problem here. Okay, so to start 28, you always start with the number in the problem, which is our 123 grams. So we write that in our first spot. So we write 123 grams of Na2S. And what we're doing is we are multiplying fractions. Remember, that's our key with dimensional analysis. So, what is the molar mass of Na2S? Let's calculate this over to the side. 1 mole of Na2S equals, how we would get the molar mass is just like we did in question 27. We add up the mass of 2 sodiums plus 1 sulfur. And if we do that, you see the molar mass of this is about 78.05 grams. Now, if I want my units to cancel here, I already had grams in the top of this left fraction. So I need grams in the bottom of this one. So I'm going to take the 78 and drag that down here. 78.05 grams per 1 mole of Na2S. Notice that grams would then cancel out, leaving us with moles, which is exactly what we wanted. So if you do 123 times 1 divided by 78.05, you get 1.58 moles of Na2S. So there's our answer for that one. For 29, similar idea. Start with the number in the problem, which is this one. So we'll take our 0.35 moles of water, which we know is H2O. But now, we didn't use the molar mass, right? We wrote to ourselves that we were going to use Avogadro's number. So our conversion factor this time is going to look like this. 1 mole of water equals 6.02 times 10 to the 23rd, and water asked about molecules, which I've always been abbreviating MC, but feel free to write that out if you would like. Just a reminder that both this and this are on your reference sheet, so make sure you check that out under the Unit 6 heading. But since I had moles up here in the top, I need to pull the mole part down here in the bottom. So make sure you're putting units with all these numbers so you remember how to arrange your dimensional analysis, but the other part of our conversion factor would go in the top. So now moles of water would divide out, leaving us with molecules. So if we plug this into your calculator, you would do 0.35 times 6.02 times 10 to the 23rd divided by 1, and you would get 2.1 times 10 to the 23rd molecules of water. Okay, my suggestion, make sure you used the E button when you entered your Avogadro's number in scientific notation there. Okay, and for the last problem of this section, we are going to do question 30, which is asking about percent composition. Now, if we had had numbers in the problem for question 30, we would just use those and do the part over the total multiplied by 100. However, we don't have any numbers in the problem for question 30. So what we're going to have to do is use the periodic table to get some values, okay? So, again, if you look on your reference sheet, pull up the Unit 6 section, and you will see a formula that says percent by mass equals the mass of element in a compound divided by the molar mass, which is what we'll use for our total, multiplied by 100. So let's jot that down as a reminder. So it's asking about each element, so we're going to need to do each of them individually. But our percent of carbon would be the mass of carbon multiplied by how many there were over our total, which we're going to use the molar mass, and then we'll multiply by 100. We will do the same thing for the other two elements as well, but replacing the top part with the mass of that one particular element. The molar mass on the bottom will not change, however. We're just essentially changing the numerator. Okay, so here's just our setup. Now let's plug our numbers in and solve, and we will be all done with our Unit 6 questions. So, for carbon, the mass of carbon off the periodic table is 12.01, but notice I have 6 of them in the formula, so we need to multiply that by 6. And our molar mass of this whole thing, if you do 12.01 times 6, the mass of carbon, plus the mass of hydrogen, 1.01 times 8, plus the mass of oxygen, 16 times 6. If you do all of that, because we'll need this anyway, you'll get that your molar mass of that substance comes out to be 176.14 grams per mole. And that's what would go on the bottom of our fraction here. Alright, and if we multiply by 100, we'd see that our percentage of carbon in this particular compound is 40.9%. Make sure we have our unit of percent on that. And now let's do the same thing for the other two. Our mass of hydrogen, 1.01 off the periodic table, multiplied by 8, because there were 8 of them in this compound. The denominator does not change because the molar mass is the same for this whole compound. We get that that's 4.6% hydrogen. And last but not least, our mass of oxygen, multiplied by 6, because there were 6 of them, divided by that continuing molar mass again, and we see that we would have about 54.5% oxygen. A good way to check if your answers make sense here is, since I calculated the percentages for all of the elements in this compound, these 3% should add up to 100, which they do, so we know that our answer is at the very least closer to being correct. That's sort of a good sign that we're on the right track. Okay? So those are all of the questions from Unit 6. The final video will deal with the questions from Unit 7, which was all about stoichiometry.